We're on problem 60. Given the equation y is equal to x to the n, y is equal to x to the n, where x is greater than 0 and n is less than 0, which statement is valid? So let's see, x is greater than 0 and n is less than 0. So the exponent is negative, but the base is positive. So I'll just tell you right now, your gut reaction might be say, oh, if I have a negative exponent, maybe I somehow end up with a negative number somehow. But you have to remember, a negative exponent, it just tells you that it's really just the inverse of the positive exponent. So this is equal to 1 over x to the minus n, right? And if n is less than 0, then minus n is greater than 0, right? So you could say this is the same thing as 1 over x to some other letter, m, where m is minus n, but then m would be greater than 0, right? So no matter how negative this exponent is, especially if this base is positive, you're going to end up with a positive number. You're going to end up with very small fractions if this gets large enough, right? It could be 1 over x to the 100th power or something. So it could be a very small number. It can approach 0, but it'll always be a positive number. So y is always going to be greater than 0. It's choice A. Problem 61. If x is a real number, which best describes the value of x for which the inequality, the square root of x greater than 0, is true? So I'm assuming we're dealing with the real numbers, and well, yeah, I guess because, you know, if I got an imaginary number here, it's actually just even hard to compare it in terms of magnitude to 0. So they're actually just asking us what the domain is, right? What x's can we put in here and get an answer that where we can make some type of sense out of this statement? So obviously I could put a positive x here, right? X could be greater than 0. Any x greater than 0 will have a square root, and all of their square roots will be greater than 0. I mean, you could square both sides of that equation, and you get x is greater than 0. Again, you could put x equal to 0 there, but then the inequality wouldn't be true, right? Because the square root of 0 is equal to 0. So if you put x is equal to 0 there, that would work. You can take the square root of 0, but it just won't make the inequality true. So x can't be equal to 0. So x could be 0, greater than 0. It can't be greater than or equal to 0. Not all values of x work. I can't put a negative number in there. And I mean, you know, they say no values of x. No, sure, we can put any positive number there. That works. So the answer is A. Next problem. Let me turn the page. All right. Okay, let me copy and paste it. Which of the following conclusions is true about the statement below? X squared is equal to the square root of x. All right, so once again, let's think about it a little bit. Let's think about it a little bit. X squared is equal to the square root of x. I mean, it works. It definitely works for the number 1, and it works for the number 0. Right? I mean, if you square both sides of that equation, you get x to the 4th is equal to x. And then if you assume, you know, x could be equal to 0, but if you assume that x does not equal 0, you could divide both sides of this equation by x, and you get x to the 3rd is equal to 1. And the only number that I know works for that is the number 1. But anyway, the statement is always true. No, it's not always true. I put a 2 there. Is 2 squared equal to the square root of 2? No, 4 does not equal the square root of 2. So the statement is not always true. The statement is true when x is negative. No, x can't even be negative. You can't take the square root of the negative number. You'd end up with imaginary numbers, and it just gets very strange. The statement is true when x is equal to 0. Sure, it could be 0. The statement is never true. No, it's true when x is equal to 0 or x is equal to 1. So the answer is C. I didn't even have to do this stuff on the side right here. But hopefully it was instructive. Next problem. I've copied it, and now I have pasted it. All right. Let me try with the larger pen. Abelardo wants to create several different 7-character screen names. He wants to use arrangements of the first 3 letters of his first name, Abe. That's why they made his name Abelardo. Followed by arrangements of the 4 digits in 1984, the year of his birth. How many different screen names can he create in this way? All right, so he's got 7. So think about it. Let's just think about each slot, right? So slot number 1, that pen's too fat. Slot number 1, slot number 2, slot number 3, 4, 5, 6, 7. So slot number 1, how many different choices can he put in there, right? He could put an A, a B, or an E there, right? So he has 3 different choices for slot number 1. I'll do that in a different color. He has 3 different choices for slot number 1. Once he picks slot number 1, how many choices does he have left for slot number 2? Well, he has 2 letters left of out of the A, B, and E, right? So he has only 2 options left. And then once he gets to slot number 3, he kind of has to just pick whatever leftover letter is there in A, B, and E. So he only has 1 option. But then when he gets to the 4th digit, now he's starting to pick from 1984. For the 4th digit, once he has 4 options, he can pick the 1, the 9, the 8, or the 4. He has 4 options. Then on the 5th digit, he would have picked one of the 4, so he has 3 of them left. By the 6th digit, he only has 2 of them left. By the 7th digit, he's forced to pick whatever's left over, what he hasn't picked yet. He has 1 digit left. So the combinations, you just multiply all of them. See, 3 times 2 is 6, times 1 is 6, 6 times 4 is 24, 24 times 3 is 72, 72 times 2 is 144, times 1 is 144. So there's 144 different screen names he can create in this way. Next problem. 64. 64. Copied it, and now I'm pasting it. A train is made up of a locomotive, 7 different cars, and a caboose. If the locomotive must be first and the caboose must be last, how many different ways can the train be ordered? So we don't even have to worry about the locomotive and the caboose, right? They're always going to be in the same position. The locomotive's first, caboose is last. So we just have to worry about the 7 different cars, the order that they're in, right? So let's talk about, it's really the same problem as the last one. It's in some ways it's a little bit easier. So let's just say that's the position. Position 1, 2, 3, 4, 5, 6, 7. And let's say we just have to decide which car we put in each position. Or how many different options do we have? So let's say we're filling the slot starting with position 1. Well, we have 7 cars to choose from. 7 cars. Right, the 7 is different from that's not including the locomotive and the caboose. Right, so we have 7 cars to pick from. We've picked one of them, then in slot 2 we have 6 cars to pick from. Slot 3 we have 5 cars to pick from, right? Because we've already picked 2. And then slot 4, 4 cars to pick from, 3 cars, 2 cars. And then slot 7, we would have already picked 6 of the cars, so whatever's left over we have to pick. So let's see what this number is. 1 times 2 is 2. 2 times 3 is 6. 6 times 4 is 24. 24 times 5 is what? 120. 120 times 6, 120 is 720. 720 times 7, I'm just going to have to do a little bit of multiplication here on the side. 720 times 7. 7 times 0 is 0. 7 times 2 is 14. 7 times 7 is 49. Plus 1 is 50. 50, 40. So there's 5,040 different ways that the train can be ordered. Let's see, next problem. Okay, maybe I'll just clear all of this. All right, let me copy the. All right. Teresa and Julia are among 10 students who have applied for a trip to Washington, D.C. 2 students from the group will be selected at random for the trip. What is the probability that Teresa and Julia will be the 2 students selected? So let's think about this. There are 10 students who have applied for the trip. 2 students from the group will be selected at random for the trip. What is the probability that Teresa and Julia will be the 2 students selected? All right, so let's think about student 1 selected and student 2 selected, right? What's the probability that Teresa is the first student? So what's the probability that we get Teresa and then we get Julia? That Teresa is the first student selected and that Julia is the second student selected. Well, the probability that Teresa is the first, well, let me take a step back. There's 2 ways that what they want to happen could happen, right? That Teresa and Julia will be the 2 students selected. Either Teresa is the first student selected and then Julia is the second, or Julia is the first student selected, and Teresa is the second. So if we figure out the probability of this happening and the probability of this happening, then we could just add those probabilities together, and then we have the probability of either of those happening. All right, so let's see. The probability of Teresa happening, so let's see, probability of Teresa is, let me do this in a different color. There's 10 students, so there's probability that we pick Teresa first. And then once we pick Teresa first, the probability that we pick Julia next, well, now there's 9 students left, right? Because you've already picked Teresa. So there's a 1 in 9 chance you pick Julia, right? So that is equal to 1 in 90. So there's a 1 in 90 chance of this happening. There's a 1 in 90 chance of that happening. And then what's the chance of this happening? What's the chance of that happening? Well, it's the same thing. This is 1 in 10, and this is 1 in 90, right? And so you have a 1 in 90 chance of it happening. And so what is the probability of either of these things happening? Of this combination or this combination? Well, you just add them together, and you get 2 out of 90, which is equal to 1 out of 45, which is choice A. And I'm out of time. See you in the next video.